Okay, so here we go. The moment you've all been waiting for in terms of antiderivatives, and I know you have in fact been waiting for this moment. We've talked about them, we've done a little bit of discovery work with them. Now I'm going to give you the official rules and everything that you can follow when we're doing antiderivatives. So this first page is some stuff that we've seen before and we talked about when we were doing the little discovery activity with antiderivatives, but it's good to have it down just so you can look back on it in your notes. So this first sentence, I've had this sentence in here for years. Antiderivatives are not scary. People get super freaked out by them as soon as they pop up and they're like, wait, antiderivatives? Like what do you mean? The only thing that I will warn you about is that once you learn the antiderivatives, you'll start to mix them up. Like you'll start to do antiderivatives when you're supposed to be doing derivatives and vice versa. That'll run its course before the AP test even happens and you'll have them straight by then, I promise. So what we're basically looking at is this. You're given the derivative and then you have to work backwards and find the original function. That's essentially what I want you to picture yourself doing. So let's look at one right here. So let's pretend the derivative of a function is secant squared. We want to find f of x. So what I'm asking you for is for a derivative, but like I said, you can think of yourself as starting with the derivative and working backwards to find the original function. So this is a derivative rule that we should know, something that we've got way back in our memory bank somewhere. And so secant squared, you're trying to figure out, okay, what function did I take the derivative of in order to get secant squared? And so that function that we're trying to figure out would be tangent. Because if you remember, when you take the derivative of tangent, you get secant squared. So what you do is you write down f of x equals tangent of x. And so it works backwards. If you're trying to figure out, did I do this correctly, you just take the derivative of tangent and you see that yes, you do in fact get secant squared. And so it's just like, do you remember when you learned how to factor things and you'd wonder if you factored correctly? All you have to do is refoil the binomials together and you'd see if you were right. This works exactly the same way. All you do is take the derivative again, because we should be really comfortable with those, and you'll see if you did it correctly. So here's an important note. This is a note that we talked about when we were doing the little discovery activity. Like, yes, f of x equals tangent works, but like g of x equals, tangent x plus 7, that works. H of x equals tangent x plus e raised to the power of pi, that works as well. So it's important to keep in mind that these work too. Okay, so we can kind of draw a conclusion from that. So the difference between this one and this one and this one is just a little constant hanging out on the end. All right, so this is an antiderivative, this is an antiderivative, this is an antiderivative. That's why we use the word an. That's why we say an antiderivative, not the antiderivative. Okay, so we say that f of x, some function notation, we say it's an antiderivative of little f of x if you take the derivative of f of x and it lands you back here at f of x. So that's just what we did up above. We say that tangent is an antiderivative of secant squared because the derivative of tangent gives us secant squared. So that capital F and that lowercase f seem confusing right now. I promise it will be just fine very soon. Okay, so here's the theorem. Let f of x be an antiderivative of f of x on, and that a to b, that's an interval, an open interval. Then, here's what we say. Every other antiderivative is of the form f of x plus c. So it's kind of what we wrote up above when we use that plus c as a constant. So let's say for some constant c. So c can be absolutely anything, a boring constant, maybe even a 0. It could be a very creative constant like e to the pi or even more creative. But the key point, and this is very important, antiderivatives are not unique. Okay, that is our key point here. There are hundreds and thousands and millions and billions of possible antiderivatives. All we have to do is switch up the constant, and of course we know there are an infinite number of constants available to us, which means there are an infinite number of antiderivatives for any given function. Okay, so an antiderivative of f of x equals 0. This one's kind of weird. What this one is saying is this is our derivative if we're trying to find an antiderivative. So we know that the derivative of some function gave us 0. Well, the only functions that give us a consistent derivative of 0 are constant functions. Okay, so that would just be f of x equals a constant. So when we say an antiderivative, all I asked you for was an antiderivative. You could say that f of x was 7, or f of x was e, or f of x was the natural log of 14, or whatever you want. But the general antiderivative, which is what we're about to write right here, we say that f of x equals c, and that kind of covers all the bases for us. So we define the general antiderivative as just that notation. That general derivative is a function written in terms of an arbitrary constant c. Okay, so general antiderivative is an antiderivative written in terms of an arbitrary constant c. And arbitrary just means it could be absolutely anything. We just leave the c there to show that any constant in the world could be in its place. Okay, so let's find a couple of antiderivatives here. Okay, so x to the negative 3/5. This is really similar to the discovery activity that we were doing. So we use capital F of x to denote antiderivatives. So x to the negative 3/5. Let's kind of work our way backwards here. So I'm going to leave a space because we know we're going to have a coefficient there. So if my derivative was negative 3/5, that means to find the antiderivative, I have to go up a unit in power instead of going down a unit in power. So my old power must have been 2/5. Okay, so that's what we're trying to figure out. And then I know when I take the antiderivative, this 2/5 multiplied out front by something, and it left me with 1. So it's like 2/5 times what would leave me with 1, and that would be 5/2. Okay, so again, really easy way to check. All you do is take the derivative of this. So the 2/5 comes out front. I get a coefficient of 1. My power drops down to a negative 3/5. That's what I'm left with here. But because it says general antiderivatives, don't ever forget your plus c. You have to have the plus c there. You will lose points on my test. You will lose points on the AP test if you do not have that c there. Okay, let's do this next one. F of x equals, again, we're going to kind of work our way backwards. So it must have been x squared. And then we're thinking, what must have been here to give us 9? So what we actually do is we take this 9 and we divide it by 2, because we know that it must have been multiplied by 2 to get 9. So that would be 9 divided by 2, or 9/2. You can always double check to make sure we get there. Then plus our next thing here, we pop the power up 1. So from negative 2, we go up to a negative 1. It's like, all right, what must have been here to get us a positive 15 after I multiply by the negative 1? That would be a negative 15. You can always double check. You'll get this derivative here. Since it's a general antiderivative, do not forget your plus c. Okay, power pops up from 7 to 8. If I multiply 8 by whatever goes here, I'm supposed to get 4. So that would be 4/8, or 1/2. Okay, and then I know the 3 is going to be there. The antiderivative of cosine is sine, because you're trying to figure out what do I take the derivative of to get cosine. So this is still a minus, and then this is sine, and don't forget your plus c. I will say this again, you can always just take the derivative of these functions that you're coming up with and double check that you're doing it correctly. Okay, one more on this page here. Antiderivative e to the x. Not only is this the best derivative ever, it is also the best antiderivative ever. The antiderivative of e to the x is also e to the x. And then this next thing here, I know I'm going to have a 4 as my constant. Whenever you have a constant there, it's not doing anything. All you have to do is just leave it and rewrite it there. The antiderivative of sine, we're trying to figure out what gives us a derivative of sine, and that would be negative cosine. So I make my positive here, cosine, and don't forget your plus c. Okay, so just a little bit of practice with some antiderivatives. That's essentially the same thing that you guys were doing in your little discovery. So let's flip over. We've got one more page we're going to work with here. Now we're going to start calling it integration. Okay, so I will say this from the very beginning. When we say antiderivatives, antiderivatives are like the noun, and integration, well, I know integration itself is a noun, but when you say you're integrating something, that's the verb. Okay, so the antiderivative is the thing, the integration is the process. Okay, so integration is literally the process of finding an antiderivative. So I'm also going to give you the notation. Now this notation we've seen very briefly before. All of it is very strange when you're not used to it, but I promise you, you will in fact get used to it. So let me write the notation. So we've got this weird little squiggly thing that looks like a strange elongated S. Jeez. So we write f of x in here. That's our function that we're taking the antiderivative of. We throw in a little dx, and then we say it equals f of x plus c. Okay, so I'm going to label everything on here. Okay, so this guy right here, that's just the integral sign, or the integral symbol, either way. This is the original function. We also call it the integrand. So anytime that I refer to the integrand, that is what is inside of the antiderivative or the integral symbol. This right here just means with respect to x. So that's what it means when you see that. What it's called is the differential. So the differential could be dx, dy, dt, d whatever. That means it's the variable for right now. It's what variable you have in the integrand. It's what you're taking the antiderivative with respect to, just like what you're taking the derivative with respect to. Okay, and then this piece of it right here is the general antiderivative. And finally, we call this piece right here the constant of integration. So lots of little pieces. So anytime I talk about the integral sign, the integrand, the differential, the antiderivative, the constant of integration, hopefully this will help you to figure out exactly what I'm talking about. All right. The general antiderivative, that's the right-hand side up here. We will also call it the indefinite integral. Okay, the indefinite integral. So I will say one or the other. I will use them interchangeably. You should get comfortable with using them interchangeably because that's what the AP test will do as well. Okay, so we've got some rules. Finally, we are going to put down some actual hard and fast rules. It's the power rule for integrals. We've kind of figured this out already. So when you're taking the integral or the antiderivative of something to a power, and of course you're taking that with respect to x, here's what we do. We've figured out that we need to pop the power back up 1. So the new power is now an n plus 1, and then hopefully we've already figured out that what we need to do with that old power, the new power, is divide whatever constant you've got there. Oops, that's an n plus 1, sorry, n. So 1 over n plus 1 times x to the n plus 1, and then of course plus c. So if you're taking the antiderivative of like x squared, that would be 1/3 x cubed plus c. If you're taking the derivative of x to the 9th, that would be 1/10 x to the 10th plus c. Figure out what you need to take the derivative of, because when you take the derivative of this, the n plus 1 would come out front, this would become 1, and then x would drop down to the n. You'd land right back here. Okay, sum and difference rule, very easy, very basic, very similar to what we know with derivatives. When you're taking the sum rule or the difference rule, when you take the antiderivative of something like this, like a function f of x plus or minus a function g of x. When it's all written like that inside of one integrand, what you do is you just split it up. You take the derivative of f with respect to x, and then you either add or subtract, depending on what you have here, the integral of g of x with respect to x. So that way when you're taking the antiderivative of a polynomial, we've already kind of been doing this, you just take the antiderivative of each piece and just add them all together. Constant multiple rule, we've already kind of been doing this too, says if we have a constant right in there with the function, it's not going to affect our antiderivative at all, so we can just throw it out front and then take the antiderivative of the function that we're dealing with. Okay, how about some trig rules? Trig rules basically are just the reverse of what we know from our trig derivatives. So trig rules, the antiderivative of sine. Okay, or what did I take the derivative of to get sine? And that would be a negative cosine plus c. Antiderivative of cosine, or again, what did I take the derivative of to get cosine? And that would be sine x, of course, plus c. And then we're just kind of matching them with the ones we know. So we know we've got secant squared. What did I take the derivative of to get secant squared? Tangent. I did that one on the front. Cosecant squared, that would be a negative cotangent, because we know the derivative of cotangent is negative, so the derivative of negative cotangent would be positive. We've got secant tangent. The function that gives secant tangent as its derivative is secant. So one last one, very similar, cosecant, cotangent, that would be a negative cosecant. Okay, so notice we do not have a general antiderivative for tangent, secant, cotangent, cosecant. We will eventually, but we don't now because we don't have any functions that give those as their derivatives. Okay, the exponential rule, of course, one of the most wonderful rules that there is. The antiderivative of e to the x is e to the x plus c. Okay, so let's take those rules. We're going to take those rules and take some antiderivatives. All right, so the following indefinite integrals. We've got new notation, official rules up here. So what gives us a derivative of 3/2? Well, a constant derivative means a linear function, and so that would be 3/2 times x, and of course plus c. Now, the fact that this dx is right here was what told me what variable to put here. If this were dt, it would be 3/2 t, etc. So right here, we're going to take some antiderivatives. So theta is our variable. So theta, the power pops up from 1 to 2, and then there must have been a 1/2 here. Okay, plus, and then what gives us a derivative of secant squared? Well, that would be tangent, and then don't forget your plus c. Okay, last one for this set. We start with 5t cubed. So let's start with the power. Power pops up to 4. And then I divide by that new power. So I'll have 5/4. And you can always double check. If you take the derivative, you will get 5t cubed. And then let's see, minus. So t, my power pops up to a -2. And like I said, I am going to divide by my new power. So my new power is -2. I'm going to divide by -2. So this will be plus 1/2. And you can always double check. Don't forget your plus c. All right, so that's it for now.